Hi, my name is Amir, and I'm gonna present to you about the introduction of this project. So, this project is we need to make sure that the structure components must be designed to safely withstand external loads and prevent failure. So, this project we investigate the behavior of the road subjected to axial tensile loading, which causes stress, strain, and axial elongation. So, in this particular case, we study involved in which is a 30 kg suspended chandelier supported by a 2-meter long aluminum rod was analyzed. So here's the two engineering solution were considered. First, which is increasing the rod diameter, which is geometric modification. And second, we replace aluminium while with mild steel, which is a strong steel, yeah, and lightweight. And second, which is okay. Now, the objective of this project is to determine the most effective design that ensure the structure safely and minimize the deformation. Thank you.
Sound Charter, my name is Nesangalan Naidot and my metric number is CD240338 and I'm going to be presenting about the literature review on this case study. So the first point I want to talking about is the basic concept about the exertensor load. What is the meaning of exertensor load? It's when a member pull in the tension, it will be create stress and strain. What is the meaning of the stress and strain? Stress is the force divided by the area. Meanwhile, the strain is how much the members stretches by divided by the original length. Both of these have a different type of the equation, which is for the stress. The equation that we use is sigma equal to P over A, which is a force over A. A is area. Meanwhile, for the strain is epsilon equal to delta L over L, meaning of changing length divided by the original length. In the elastic region, the stress and strain follow a straight line known as a Hooke's law. What's the meaning of the Hooke's law? It's to calculate exactly how much the member stretches. And in the Hooke's law, we usually using a formula theta L equal to P times L over A times E, where the E is representing the material stiffness, A is for area, P is obviously as a force, and L is a length. In our engineering world, we're always talking about the safety. So to keep our design safe, we apply this safety factor, which the yield strain divided by the working stress. And this safety factor is to ensure that we never reach the point where the material is permanently formed. For the second point is we're gonna talking about the different material behavior differently. So I'm gonna talking about the three type of material, which is metal, composite, and concrete. For the first type is metal. Metal we usually know as a very tough material, and the behavior of the metal is when we stretch elastic first at the first place, it's become a plastically, and they become a neck down, finally become a fracture. Meanwhile, for the composite, they are rely on their fiber for strength and can fail by fiber breakage or matrix cracking. For the last type of material I want to talking about is the concrete. Concrete behavior is weak in tension and show the strength is little bit of sustaining. That's why the material selection is very critical. As the other example I want to talk about is my strength, my steel, sorry, is for strength. Meanwhile, for the aluminum is for the lightness. So it's depend what type of the material they want to use it. Finally, for the third point I want to talk about is the real life application about the exertensor load. I want to take an example as suspension bridge cables. Why I take it? as my example because this cable support the bridge deck and it's also support the traffic load, and these two scenario will experiencing axial tension. They are made from the highly strength steel wire can safely elongate under load without permanent deformation. We as engineer apply an adequate safety factor to ensure the stress stay below the restraint and also preventing any catastrophic failure. That's all from me. Thank you.
Assalamualaikum. My name is Ilham bin Marhuni and my matrix number CD250197. Next, I will explain about problem statement. For our case study, the facility management need to vertically suspend a heavy industrial chandelier with mass of 30 kilogram from a rigid concrete ceiling in a main mall. The structural member available for this is a solid, uniform rod made of low-grade aluminum alloy. The rod has a longitudinal length of 2 meter and cross-sectional diameter 3 millimeter. The engineering team must decide between two fundamental interventions to satisfy a target factor of safety of 2. Next, we list all the parameter given from the statement like suspended mass of 30 kilogram, original rod length 2 meter, rod diameter 3 mm, modulus of elasticity for aluminum alloy 70 gigapascal, material yield strength 50 megapascal, and target safety factor is 2.0. Next, when we try to identify the value of parameter given past the target safety of factor of 2 or not, first we need to calculate the value of area for the rod. The area is 7.0686 times 10 power of negative 6 meter square, and value of F using formula W equal mass times gravity 30 kg times 9.81 meter per second square, and we can get the answer is 294.3 Newton. And then when we want to calculate the value of normal stress using formula sigma equal F over A, we can get the normal stress of the parameter is 41.63 megapascal. And then we try to identify the safety of factor using formula sigma yield over sigma actual. We can get the safety factor for the parameter is 1.2. So we can see that the safety of factor does not pass the target of 2. And then when we try to calculate the value of elongation using formula delta L equal PL over AE, we can get the answer is delta L equal 1.19 millimeter. We have two options of solve the problem for our case study. First, option A is modify cross-section area. We need to identify the sigma allowable using formula of safety factor. We rearrange the formula and we can get the sigma allowable is 25 megapascal. And then using formula of normal stress, sigma allowable equal P over required of area. And required area, we can get 1.1772 times 10 power of 5 meter square. And then using formula of cross-section area, we rearrange to identify the new diameter and we can get 3.87 millimeter. When we try to identify the elongation of the material using formula delta L times PL over A required times E, we can get the delta L is 0.714 millimeter. For option B, we modify the material properties. We choose mild steel with sigma yield of 250 megapascal and elasticity of 200 gigapascal. The area and the sigma actual same like the baseline state of the parameter. So we directly calculate the safety factor 250 megapascal over 41.63 megapascal, we can get the safety factor of the modify the material properties is 6. So we can see that the safety factor is 3 times more than the target. And then calculate the elongation, we can get delta L equal 0.416 millimeter. So this is the summarize of our result for case study. Our evaluation of the initial baseline state, which used a low-grade aluminum alloy with a 3 millimeter rod diameter, showed that it was unsafe, yielding a weak factor of safety of 1.2 and a high axial elongation of 1.19 millimeter, leading to its rejection. To fix this, we explored two options. Option A, geometric fix, increase the rod diameter to 3.87 millimeter using the same aluminium, lowering the stress to 25 megapascal, and successfully raising the factor of safety to an accepted 2. Meanwhile, option B, material fix, keep the original diameter 3 millimeter, but swap the material for mild steel, which drastically improved the factor of safety to 6 and cut elongation down to just 0.416 millimeter. Ultimately, because of its superior strength and minimal stretching, option B was selected as our final design choice.
Hi and Assalamualaikum. My name is Muhammad Haris Shami and my matrix number is CD250304. And as for my part, I will talk about discussion. The initial component was highly unsafe, achieving a safety factor of only 1.2 under a 30 kg load because idealized formulas ignore real-world weak spots and dynamic forces. To fix this and reduce structural stretching, option A, increasing part width to 3.87 mm, was compared against option B, switching the material to heavy mild steel. Option A was selected as the optimal solution because it perfectly hits the required 2.0 safety factor and lowers stretching to 0.714 mm without the massive weight and cost penalties of option B. This choice perfectly demonstrates the fundamental engineering balance between geometry and material selection to safely protect against unpredictable real-world operating conditions. That's all for me. Thank you.
In conclusion, this analysis shows that several factors affect the stretch and deformation of a component, including the applied load, material properties, cross-sectional area, and length of the material. We also learned that excessive stress can lead to component failure, which may reduce safety and reliability in engineering application. Therefore, selecting suitable material and design component properly are very important to ensure safe and efficient performance. In addition, increasing the material strength or cross-sectional area can help reduce both stress and deformation, making the component more durable. Overall, stress analysis is essential engineering tool because it helps prevent failure, improve performance, and ensure that structure and mechanical component can operate safely under different loading conditions. Thank you.